Hello and welcome back. In today's video, I'm going through exercise 1.25 from the Art of Electronics. And in this exercise, we need to show the series and parallel capacitor equations and derive them from the rules that are given to us in the paragraphs above. So I will briefly explain the rules that are given to us and go through the equations that are mentioned on the screen right now. So 1.17 and 1.18. Obviously, feel free to go through those equations in your own time as well. And then I will show you how to get to the series and parallel capacitor equations. So let's get started. Firstly, I will go through the series capacitor equation. So this is basically when you have two or more capacitors connected in series and you are measuring the total capacitance, or you are interested in the total capacitance across all of them. So the equation given to us in formula 1.18 is the total capacitance is equal to 1 over C1 plus 1 over C2, and that goes up to Cn. So depending on how many capacitors you have. Now to derive this formula, there is two things that we need to use. In the book and the paragraph above the question, we are given this equation here, which says that the impedance Z of a capacitor is equal to 1 over j omega C. C being the capacitance and omega is frequency in radians, which is equal to 2 pi f. The paragraph above the question also gives us the total impedance of series components or devices, which is Z equals Z1 plus Z2 plus Z3. So obviously you can see that this Z here will plug into this equation. So let's do that now. So Z total, or total impedance, is equal to Z1 plus Z2. And plugging in this formula over here and denoting the two capacitors that we're using for this calculation as C1 and C2, we get, so replacing Z1 with this formula, we get this. So 1 over Z omega C1 plus 1 over Z omega C2. And then if we rationalize that, we can basically bring out 1 over Z omega on the outside and keep the capacitances on the inside. So you can see over here that I have generalized the formula to include Cn as well. But it's the same solution if you use two capacitors or more. The next thing I will do is basically the total Z, I've turned that into this equation as well. So I've got 1 over j omega C total, which is what we're trying to calculate. Now, if we multiply both sides by j omega, we get rid of the j omega on this side and we get rid of it on this side, and we end up with the equation that you see over here. So you get 1 over Ct is equal to 1 over C1 plus 1 over C2 plus all the way up to Cn. And then if we bring the C1 by itself, we get to the equation that we are after, and that is given to us in equation 1.18 in the book, which is that the total capacitance is equal to 1 over C1 plus 1 over C2 all the way up to Cn. So this is the solution for the series capacitance formula. Now let's look at the parallel capacitance formula. So the impedance of the capacitor is the same as before, so that is 1 over j omega c. However, the parallel impedance formula is now different, so we're using the total impedance is equal to 1 over z1 plus 1 over z2 plus 1 over z3 all the way up to however many capacitors that there are in the circuit. Now, if we're looking back at equation 1.17, the total capacitance of capacitors connected in parallel is equal to C1 plus C2 plus C3 all the way up to Cn. So what we are going to do now is plug the impedance of a capacitor into the equation that's given to us on 1.31, and we get the following. So you can see this equation is the same as this one. And then what I've done is basically plugged this, so 1 over j omega c, into all the z's that we see on the equation. And obviously you get 1 over 1 over 1 over. So it's in, basically you get 1 over 3 times, but looking at just the z1, you get 1 over twice. So they cancel each other out, and you get j omega c1 plus j omega c2 all the way up to j omega cn. Now, if we rationalize that out, we get j omega, and in brackets we can put down c1, c2, cn, and that's the equation that's given to us at the end there. Now, turning the right hand side of the equation from impedance to the capacitor formula, we have 1 over j omega ct is equal to 1 over j omega, and in brackets c1 plus c2 all the way up to cn. Similar to before, if we multiply both sides by j omega, we get rid of the j omega on both sides, and we end up with 1 over ct is equal to 1 over c1 plus c2 all the way up to cn. And bringing the CET by itself, we get the total capacitance is equal to C1 plus C2 all the way up to Cn. You can see this formula matches the formula that was given to us earlier in the book at equation 1.17. So this is the full solution for this question. Hopefully that was useful. If you have any questions, please let me know in the comment section below. Over 1 over 1 over 1 over 1 over 1 over 1 over